All right, sorry for the interruption. So we are going to continue where we stop. So I'm still talking about I'm still on Mendeleev. Like Mendeleev was one of the scientists, like in fact the major one, that received credit for the work on the periodic table. And I said that he also uses atomic mass like other people, but one of his own uniqueness is that he was very specific, and he grouped the element in a way that is very well arranged in groups and in periods. But we must also talk about the limitations to his this thing, and which I've already discussed about, that Mendeleev theory is actually deficient because it does not account for noble gas and some other elements that we later know today as lactinides and actinides. Well, the periodic table is not perfect until the emergence of Moseley, and it was him in 1875 that perfected the work of Mendeleev, and then it was the one that perfected the work of Mendeleev, and he actually used atomic number to group the elements in the periodic table instead of atomic mass. And since atomic number follow a sequential order, so there's no how I will have arranged the elements in the periodic table and placing the bigger one after the smaller ones. It's not possible. So through the atomic number, we are able to arrange the elements in a correct and more accurate manner. So the cobalt and the nickel that are counterfeiting each other, the later gets back to the right position, and tellurium and the iodine, as well as the potassium and argon. So this work of Moseley is what led to what we called the modern periodic law. And what is the modern periodic law? The modern periodic law states that the chemical reactivities of all elements is a measure of their periodic function. And it's the periodic function of element is a measure of the atomic number. That means atomic number is a more fundamental particles of an element than any other thing. So the atomic number is more important than atomic mass. So atomic number is their periodic function. That means the behavior and how elements combine depends on the atomic number. And that one will now lead us to the grouping, which he did like this. Then he created, and this modern periodic law by Moseley, when he uses the atomic number instead of the atomic mass, actually led to the discovery of the modern periodic table and through the modern periodic law. And he grouped the elements into, just like Mendeleev has done, into rows and columns. And this is row 1, row 2. Then he bridged it at the center. He bridged it at the center, and he called these people transition meters. Transition meters. And the work of Mendeleev only highlights a few of them. Then he called this column 1 the group 1, then the group 2, then the group 3, the group 4, the group 5, the group 6, the group 7, and the group 8. Now he grouped all the elements in the periodic table into 8 groups, and then he made the rows, which is the period 7. So now he began to place that. He said hydrogen is the first known element, and helium is the second known element, but it is a noble gas. It's not reactive. So it sees that it behaves like elements in group 8. Then they place it here. So, and this number are sequential. So this table is better than Mendeleev's table because he noticed that helium is in group 8. He rather leave this place empty than to just fix any element inside. And then if you can remember, you know that yes, hydrogen, helium. Then from here you have your lithium and down to calcium. So, and this is the periodic table. But these people at the middle here did not have a specific oxidation state like valency. So because they used to change, we have copper, they are part of transition metals, the gold, the silver, and others. So they have variable oxidation state. So the word transition means they change more often. So they are not fixed. So all these elements that are put in a specific group, there's a reason for putting them, because these elements, they used to exist in a specific oxidation state. That means all elements in group 1, they have 1 valence electron. All elements in group 2, they have fixed 2 valence electron. But all these transition metals, their own is not fixed. Sometimes they can exist in +1, like gold, +1, +2. Then sometimes they can exist as +3. So they change more often. And that's why, since there's no group that can actually contain them, so we have to bring them together. And if you can check your periodic table, you can, after this, you can go and check your periodic table. You can go online, find, like, just press the image of a periodic table. You will see that these elements occupy 10 rows in the periodic table. So in the Moseley periodic timetable, he grouped them in 8 groups, and then he leaves these 10 rows as a space in between them. But in the modern periodic law, we now later see that there are some things that is not accounted for because of this space that was given. Because there are some elements that not behave alike, like those ones that are on the upper part of their groups. So we call those ones group B, group A. So, and there are some elements here that behave like some of the elements here in the fifth group. So to avoid that, we now say, okay, don't let us separate the transition methods as a different group, that they are not in a specific group. So let's just say we have 80 groups in the periodic table. And how is that possible? Since this is 1 and 2, and I said these people are 10 rows. So if you add the 10 to the 2, that's 12. That means your group 3 is then 13. And if you count down to group 8, then we have 18 groups. So now, in modern periodic law, the current groups in the periodic table is 18, which accounted for our transition methods. That means your group 1 to from group 1 to 8. So 1 is still 1, 2 is still 2. But your 3 now become 13 because of the addition of the 10 rows transition method. And that is one of the periodic table. So the next thing I will show you now is to show you how we can actually account for the combining power of each groups in the periodic table. Don't forget that in the modern periodic law, we said periodicity is the function of the atomic number. So the way elements behave, the way they react, the way they do, depends on the group they belong, and that groups indicate the atomic number, because there's a reason why they are in those groups. Now, but if I fill this table completely with my first 20 elements that we know, your hydrogen to calcium. So this is hydrogen, helium. So if you fill this will be element 3, which is lithium. If you fill this will be lithium, beryllium. Beryllium is 4. Boron is 5th. Carbon 6th. Nitrogen 7th. Oxygen 8th. Then fluorine 9, right? Then neon is 10. Then this one here will be what? Will be sodium, which is 11. Then beryllium, we'll be having magnesium as the next. That's 12. Then boron, we'll be having aluminium as the next. That's 13. Carbon, we'll be having silicon. That's 14. Then this one we'll be having phosphorus, which is 15. Oxygen, we'll be having sulfur, which is 16. Fluorine, we'll be having chlorine, which is 17. Then we'll be having argon, which is 18. Then we now have our potassium, number 19, and our calcium, which is 20. So we can stop here because I'm only concerned with the first. We are so familiar with the first 20 elements, and they are here. So I hope we are following. Please, if you are following, you can show some signal that you are still with us. So this is the first 20 elements as shown in the periodic table when we did not include transition methods. Now we notice that if we still go with the Mendeleev and the Moseley periodic timetable, while we are not saying we have 18 groups, we have 8 groups, I can actually account for the valency of all the groups in the periodic table, apart from the transition methods. Now, that means from group 1 to our 8 in Moseley timetable, I can actually account for their valency. But before that, I said earlier that these rows are the period, row 1, row 2, row 3, row 4, up to 7. So they are the period. But we cannot use period 1 to represent all of them, because right now I'm going to configure them. Because period 1 is not having elements in group 2, in group 3, in group 4, down to group 6, to group 7, no element. So I cannot use these two just to represent everybody. So the best period to use to represent stuff like that is let me use period 2. Now, if I take someone out of each group, that person accounts for all of them. That means anything I said about that person is for all. All right? Now, let's talk about lithium. If I bring out lithium which is having an atomic number of 3, you will see that lithium, if you want to configure lithium, because they are in period 2, that means there's a shell before that period, because the period represents the number of shell. So lithium is in period 2, and I've already stated the reason why I'm using period 2, because it contains members in each group. So now, if you draw the structure of lithium, you cannot just draw a circle, because this circle means lithium is in period 1. But you have to draw 2 circles, showing that period is in, and lithium is in period 2. So now, that means for us to get to this atomic shell, we have to fit some electron here. And those electrons will be actually picking after helium, because the maximum element that exists here is the element with electron number of 2. So that means I have to take 2 out of this 3. So the remainder will be 1. I can put it here. So if you can see, you see that when we talk of valency of elements, if you don't know before, we are simply talking about the number of electrons in the atomic shell. So what makes them to be in those groups that they belong to is because when we configure them in this manner, the number of atomic shell that was there was the number of their group. As you can see now, you will see that from 3, as I remove the lower shell from it, which is 2, then I have 1 left, and that's why lithium is in group 1. That means if you configure the structure of sodium 2, let me take that to just confirm what we are doing. Sodium is no longer in period 2. Sodium is in period 3. That means you have to draw 3 circles. And then, of course, I said this smaller one will always take 2 because it's picking after helium. So if you take 2, this is not very clear. This is 11, okay? So now this is 11. So if you take 2 out of 11, you have 9 left. And the next shell, the last element here, reach up to 10. So this shell always contains 8. You have to know that we have this shell drawing K-elemental shell. So 8. So 8 plus 2 will be 10. So the remainder from that 10 is, from that 11 is 1, just 1. Right? So this last one makes sodium to be in group 1. So I can actually account for all of them, the way they behave in each group, by configuring their structure. Then let me be fast about this. So if I'm doing for beryllium, of course, you know that beryllium will be like this, because beryllium is number 4. Beryllium, which is 4. Then if I'm configuring for boron, boron will look like this: 2 inside, then 3 outside. And you cannot see the reason why boron is in group 3. If I'm configuring for, this is boron, then the carbon is 6. So carbon will look like this: 2, 3, 4. You will see that there is 4 unpaired electrons in the atomic shell of carbon. That's why it's in group 4. So if I'm configuring for nitrogen, nitrogen is going to be having 2 electrons inside, because nitrogen is 7. So nitrogen is 7. Let me write this here. Then if it's having 2 inside out of 7, that means we are going to put 5 outside. 3, 4, 5, 4. Okay, 5 outside. So the number of atomic shell in nitrogen is 5. That's why nitrogen is in group 5. Then if I'm configuring for oxygen, 2 will be inside. Then the remainder from the 8 we put outside. 1, 2, 3, 4, 5, 6, 7, 8. You'll be wondering why since I know that I put 8 outside, why can't I just put it double? And I'm just putting it singly. There are some rules that guide configuration. And one of the most important rules is Ohm's rule. And Ohm's rule tells us that whenever you are sharing an electron, don't be in haste to just put like them in 2s. You must first share it singly before pairing up occur. And that's why I'm sharing it 1 by 1. So if you ever see me sharing, maybe writing 2 in a side or doing it at the side, it's very, very, very wrong. I have to actually do it 1 by 1 and show that I'm following Ohm's rule. Because those rules must be in your mind anytime you are doing configuration. All right? So now, if this is for oxygen, oxygen is having 8, right? So this combination will be wrong because it's going to be having 6 then. So if we pick 2 out of the 8, we're having 6 left. So following the Ohm's rule, sorry I did not mention it earlier. So that means you draw a small shell. You will put 2 electrons because they are picking after helium, because there's a short shell before the period 2. Then if you now draw the atomic shell, that means you have removed 2 from 8. So the leftover will be 6. So following Ohm's rule, 1 by 1. 1, 2, 3, 4, 5, 6. But I want you to notice something very, very, very unique here. You will notice that when I'm configuring from lithium, which is 3, I think let it be here. So lithium, which is 3, which is having atomic number of 3, 4, 5, 6. That means this person is in group 1, group 2, group 3, group 4. We are not checking the number of protons, we are checking the number of electron in the atomic shell. Group 1, 1, 2, group 2, 1, 2, 3, group 3. Carbon 1, 2, 3, 4, group 4. You will notice that no electron in the atomic shell is paired, from lithium to carbon. But you notice that once I started configuring nitrogen, which is in group 5, I noticed that there's a place in the atomic shell where I have 2 electrons S16 together at a time. Then in oxygen, I have 2 places whereby I have 2 electrons S16 together on the outermost electron in a shell. Now, these things are not just irregularities, they indicate something. They are called lone pairs. Lone pairs, because very soon after this, I'm going to be talking about periodic properties, properties of the periodic table, about electropositivity, electronegativity, and the likes. And your understanding of this concept will help you to know why some elements are having plenty electrons, are more electronegative. So what makes an element electronegative? I'm going to be saying that later on. But I just want to understand this thing, that the modern periodic law that says that the periodic behavior of all elements in the periodic table is the measurement of their atomic number. And atomic number is also called proton number. And every element, your number of atomic number or proton number is also your number of electrons. Because don't forget that in the structure of an atom is a spherical ball that contains a centralized nucleus. And inside the nucleus, we have positively charged proton and a negatively charged neutral neutron. Then outside, we have electrons that are surrounding the protons. That means in chemistry, is telling us that what makes an atom neutral. Because as a whole, an atom is a non-neutral species. It is neutral because there's a balance between positive charge and negative charge. That means for all these electrons, there's actually a specific number of protons. That means for any element, the number of its proton is also the number of its what? Of its electron. So that means if you are saying atomic number, and we are now using that atomic number to do electronic configuration, we are not wrong, because your number of proton is also your number of electrons. Because if you have 3 protons positively charged, if you have 3 electrons that are also negatively charged to balance the charge, and that's what we are saying. So electronic configuration, you don't need to be cramming number of electrons. So once you know their proton number, according to their arrangement in the periodic table, that's their electrons, right? So now let me be fast about this. So let's configure fluorine. Fluorine, which is 9, we actually have a shell that we took 2 out of 9. Then the leftover will be 7. Then we are going to be 1, 2, 3, 4, 5, 6, 7. You notice that the double pairs, the lone pairs, the people I call lone pairs, have been increasing from nitrogen down to fluorine. You will see that here now I have about 3 places in the atomic shell whereby I have 2 electrons existing together on an atom, and we still call them lone pairs. Then finally, the noble gas, which is the neon. So neon is having atomic number of 10, which is also the electron number, and that's why we are using that number to configure it. So if neon is 10, it's going to have a subshell of 2, then the atomic shell will be carrying the remainder, which is 8. 1, 2, 3, 4, following Ohm's rule, 5, 6, 7, 8. That means all the sides of neon is in pairs. Now, you will notice that we can now make a general conclusion from what I've shown. From group 1, which we have lithium representing them, to group 4, there's no lone pair. And that's why you can actually say that whenever there's no lone pair on atom, you can say that those group of atoms, they be bonding the number of bonds of their groups. That means everybody in group 1 likes to bond 1 bond. So you'll have been seeing hydrogen in association with other elements. You will see that in hydrogen chloride, hydrogen is just 1, because chlorine is in group 7, and chlorine has 3 lone pair and 1 bonding electrons. So if they are bonding with hydrogen, they just bond with 1. So all group 1, lithium, sodium, that means I can replace hydrogen with sodium. And I think you are familiar with this, sodium chloride. So all of them, they like to bond 1 bond because they are in group 1. Group 2 like to bond 2 bond. You'll have seen something like this, CaCl2. So these 2, when in bonding, when you bring your bonding capacity and I bring my own, we are going to exchange. So if chlorine is in group 2 and they like to bond 2, calcium is in group 2 and they like to bond 2, and chlorine is in group 7, which like to bond 1, because there's 3 lone pairs. And 3 lone pairs means 6 electrons. So if minus 6 from their group 7, they are bonding 1. So they are going to exchange this figure, and it's going to now become CaCl2. And that's why you see that anywhere calcium is bonding with electronegative element, that electronegative element will be required in 2 places because calcium is in group 2. So that's why we say that the periodic function of all elements is a measure of their groups. And that measure of their groups is true atomic number that we assign it. So that's why atomic number is very, very important. And that's a contribution from Moseley. And we can now see from this my structure that from group 5, which we have nitrogen as a representative member, to group 8, there is 1 or more lone pairs. And therefore, let me now explain this phenomenon. What is electropositivity? I will not like to clean this thing yet, the structure yet. Electropositivity, I want to believe we are seeing this. All right. Now, these 2 things are periodic functions. They are periodic properties, and there are 2. We believe that all elements in the periodic table are either electropositive or electronegative. So what is electropositivity? Electropositivity is actually depicting that you are not having enough electrons. You are lacking electrons. While electronegativity means you have excess electrons. And we notice that when you move from left to the right of the periodic table, the elements we are seeing at the right-hand side, nitrogen, oxygen, fluorine, just take this structure to get it. The extreme ends here, nitrogen, oxygen, fluorine, and neon, if they are representing their groups, they are more electronegative. Why? Because they are the people that we can see that they have lone pairs. For you to have lone pairs, you have double. It means that you have plenty electrons. So these people are rich in electrons. So they are called electronegative species. And they are also called non-metals. So non-metals are majorly all these people, nitrogen, oxygen, fluorine, and they are highly electronegative. But if you can see these people, the electron is not even circulating. It's not distributed symmetrically. Talkers of they have pairs. They don't have. So they are very poor in electrons, and that's why they always they are poor, and that's why they always show positive. So if you want to see sodium in its ionic form, which is in group 1, you've seen it as Na+, because that plus is showing that they are poor in electrons. So they'll be looking for someone which is electronegative to give to them. Normally, we know that in normal life, addition sign indicates that you have excess, and minus sign indicates that you are lacking. But in chemistry, it's not so. In chemistry, if you are positive, it means that you are lacking electrons. If you are negative, it means that you are rich in electrons. And why? Now, if we know that, okay, I'd like to clean this so that I can explain that. Now, I'm trying to give you a physical illustration. Now, if in normal life, you know that positive indicates addition, that if they give you more now, it adds to what you have before. And if they collect from you, it takes away. But in chemistry, it is not so. Why? Because, let's say, for instance, the concept of an atom is like a spherical ball that contains the proton and the electron. They are the charged species. Since the neutron is not relevant, so let us use 0 for that. Is a neutral species. So this is a neutron. Yeah. This is the electron, which is negatively charged, and this is the proton. Now, if you are positively charged, that means proton is more than your electron. So if sodium is carrying Na+, that means the atom of sodium has lost some electrons. So now there's now an imbalance between the number of proton and electron. So the atom will assume the charge of the plentier atomic particles. Let's say for instance, this structure have 8 electrons and 7 protons, 8 protons, because I said that the number of electrons was equal to the number of protons in a neutral species. Because since proton are negatively charged, proton are positively charged, the electron are there to counterfeit their charge and make it neutral. So that means I need 8 electrons to neutralize 8 proton. But if this guy now involved in this sodium, let's say this is, okay, element with atomic number of 8 is oxygen. So let's just use oxygen. So if oxygen is having 8 proton, 8 electron in its neutral state, that means the atom is neutral, it's not charged, because the number of proton has neutralized the electron. So, but if this oxygen now wants to involve in bonding, it has to actually open space for more bonding. That means if this oxygen lose electron, let's say this oxygen lose 1 from 8, that means the ratio of electron to proton will become 7 to 8. That means in this molecule, the number of protons has superseded the number of electrons. So it's going to be positively charged. So positivity means loss of electrons in chemistry. But if instead of losing 1, this atom gain 1 electron, that means the balance, the charge between electron and proton will be about 9:8. Because if I add 1 to 8, it becomes 9, and then 8 still remain 8. That means in this atom, this number of electrons is more than the number of protons. So the atom of oxygen will assume a negative form. So if you see O minus, it means I have gained extra electron that make the imbalance between electron and proton. That means I'm having more electron than proton. So that's why it's been negatively charged. So this negatively charged or positively charged does not actually indicate our normal addition and subtraction. It's indicating which of the subatomic particles between proton and electron is more in that species. So if you have negative, that means there's plenty of electrons. If you have positive, that means there's lesser electrons compared to protons. And that's why we have that. Please, are we together? I believe you are still following. Please, if you are following, please, you can give a signal so that you are following. All right? I hope you understand. So that means metals are electropositive because they have more protons than electrons. Why non-metals are electronegative? Because they have more electrons than metals. And that is why we always know that elements that carry negative, they are highly electronegative. And that's why you'll be seeing all these elements. You have been seeing OH minus. Why is it minus? Because there's an element that is in that group of lone pairs that is present. Oxygen is in group 6. Now, let me now summarize this thing for you before I now talk about periodic properties. Now, the summary of what I've been saying since morning is that the periodic table is grouped into 2 groups majorly. You have the metals and the non-metals. Then subsequent discovery, now notice that this is the first discovery. In the second discovery, we now notice that there are some elements that exist as bridge between the 2 of them. They are not metals and they are not non-metal. So we call them metalloid. That's in another generation. Then the non-metals still exist. Now, we now shows that elements that are in metals, they are from group 1 to 3. While elements that are called non-metals, they are from group 5 to 7. Why we now have another element that we call the noble gas. Right now, this is now the modern, so that you can, before it exists as 2, 1, 2, then later on we now have 1, 2, 3, then we now call this one noble gas. 1, 2, 3, 4. Then noble gas are group 8. Now, I quickly explain what I mean. That means from group 1 to 3, there's no lone pair. If you configure them, if you can go back after what's this, and you can go back home and draw the structure of, just take one person from group 1, 2, and 3. You will see that in the atomos share, there will be no lone pair. But metalloids too, there's no lone pair. But all the sides of the atomos electron, or of the atomos shell, is singly bonded. So there's no free side, there's no free end. So they exist as a gap between metal and non-metal. Because the highest electrons an element can have, like that can complete, stability is in 2s. You have duplet state and octet state. Is either you complete 2 or you complete 8. So carbon is actually halving it. It's getting half of it. So it is in between metal and non-metal. So they are metalloids. Carbon is an example of such. Carbon, silicon, and others. So from group 1 to 3, no lone pair. From group 5 to 7, there's 1 or more lone pair. That means if you correlate this thing together now, you will see that metals are the guys without lone pair, while non-metals are the guys with 1 or more lone pairs. And then example of lone pair element is nitrogen representing group 5, oxygen representing group 6, then chlorine representing group 7, representing group 7 chlorine. That is why all these elements, whenever they are bonding, these will be negatively charged because they are non-metals and they have one or more lone pair. But you can just say like this, group 5 has one lone pair. So, since I said, since lone pair increase in sequential order, that means group 2, group 6 will be having 2, while group 7 will be having 3 pair. Now, this number of lone pairs are the number of bonds they are not going to bond readily. This number of lone pairs are the number of bonds they are not going to bond readily. That means whenever you want to talk about the bond that nitrogen likes to bond, you are going to actually find the number of lone pair it has. And pair means 2. So one lone pair means 2 electrons. So if minus 2 from 5, that means the number of bonds that nitrogen will be bonding on the normal condition will be 3. And that's why you have seen in ammonia, NH3. Why is nitrogen bonding 3 in ammonia, even though it's in group 5? It's because there is already one lone pair. So if minus one lone pair, which is 2 electrons from 5, you are going to have 3. That's why nitrogen prefers to bond 3. So you see that our knowledge of the atomic number is actually very, very good because all these things we are getting into their atomic number. Because we know that atomic number of nitrogen is 7. Then after we remove our subshare, which is 2, we have our leftover. So that's the importance of atomic number. Now, chemistry now is now the association between this guy at the left and these guys at the right. So the metalloids are just bridging them. So if sodium reacts with chlorine, we have sodium chloride. So that's chemistry. If you see any chemistry today, organic chemistry, everything is the combination or the association between the metals and non-metals. Just like everything that happened in the biomass is the association between man and woman. So and that's it. But we have some people that are in between, and they are the things we interact with, the non-living things, the thing we use. But everything that happens in this planet Earth is between 2 persons. So that's what happens also in chemistry, right? So I believe you understand all terminologies. So just try to go and sit down with it and the likes. So finally, as we'll be calling it today, I'm going to be talking about atomic properties and their trends in the periodic table. Their trends in the periodic table. I will talk about these 3 things: electron affinity, electronegativity, then ionization energy. All right? So I'll be talking about these 4 atomic properties. We call them atomicity or the periodic properties. Now, you'll be hearing all those terminologies whenever you come across periodic table: electropositivity, electronegativity, electron affinity, and ionization energy. And I've already made mention of what is electropositivity and what is electronegativity. I have told you that electropositivity is associated with metals because they are positively charged because their protons is more than their electrons. That means they have loose electrons. Then why the metals are negatively charged? Because they have gained electrons. But if you now checked with the table I give to you guys, you will see that the metals fall at the left-hand side. Then there is a bridge, while the non-metal fall at the right-hand side. So you can actually now keep a periodic trend statement and said that when we move from the left to the right of the periodic table, since I said electropositivity is assigned to metal and electronegativity is assigned to non-metal, so you can say that when you move from left to right of the periodic table, electronegativity increase. But and they can say it in another way. In your test or exam, they can ask you in another way. They can say when you move from left to right of the periodic table, or when you go across the period, what happens to electronegativity? So when you move across the period, what they are saying, in other words, is that when you move from left to right, that means if you move from group 1 to group 8, where we have the noble gas, what happened? Since those non-metals are found mostly here, so the answer will be electronegativity increase. So let me just write them out. Across the period 1, across the period, negativity increase. Number 2, across the period also, electropositivity decrease, since they are against each other. Electropositivity decrease. Then that is about the period, when you are going across the period, right? Now I'm going to talk about the group. Now, groups are, period is in rows and group are in column. That means if you go down the group, you have to go down, because vertical stuff, you have to go down. That means you are going to be using words like down the group, because the atomic size will begin to increase. So electron will not have more grip on the nucleus. So they are going to reduce the number. That means down the group, the opposite of what happened here happens. Down the group, electronegativity decrease. Electronegativity decrease. Why the other guy, which is our electropositivity, increase. Down the group, electropositivity increase. All right, electropositivity increase. So they can test you on all this knowledge about these two properties, and said across the period, electronegativity dash increase. Across the period, electropositivity dash decrease. So at least now you can answer them. Down the group, what happened? Electronegativity decrease, because when you go down the group, the number of shells increase. Then definitely you are going to see that the electron will lose grip of the nucleus. So that means they decrease down the group. Why the electropositivity increase down the group. So that is that about that. Then these two, what is electron affinity? Electron affinity of any element is measured by its ability to accept electrons. So we have some metals that attract electrons than each other. Then we have what we call ionization energy. This one is a very, very important phenomenon in chemistry, and as a chemist, either you are pursuing a career or not, once you are doing chemistry, I want to surge ahead, you have to understand that concept. From the name, ionization energy. So the word ionization is from the word ionize, and if you are ionizing, that means you are splitting into charge. Now, ionization energy, the word energy is the ability to do work. So that means there is a work that is to be done with this ionization. So if we are talking about ionization energy, that means it's the energy required to do a work. And what is that work? I'm going to explain. That work is a work of ionization. We know that if elements lose electrons, they are going to become ionized. And if they gain electrons, they are going to become ionized. All right? So ionization energy now is not the energy required to make an element ionizable. That means electrons are arranged just like orbital. Let's use BE to represent electrons, E1, E2, E3. Now, your ionization energy is the energy required to remove the closest electron to the nucleus. Because we believe that this person is more closer to the nucleus, where we have the proton, and it's very, very tight. It has a very great grip on it. So we are not concerned about this one that are far away from the nucleus, but the energy required to remove one electron from the closest electron to the nucleus from an atom is called ionization energy. And of course, if you remove an electron from an atom, it's going to become ionized, and then more protons will be more than the electrons. So I'm going to be stopping here for today. Thank you so much for watching. So please share to your friends. This is a very, very, very rich content. Share to your friends across the globe, and then you can actually drop your comments, your comments in the comment section. God bless you. Thanks so much, Joel Academy, for the invite. God bless you. Looking forward to work with you the more. Thank you so much. God bless you. Goodbye.